Hello guys, in this video we are going to discuss the solution of the problem paths to reach origin. So let us look at the problem statement. The problem statement says that you are standing on a point x, y and you want to go to origin 0, 0 by taking steps either left or up. That is, from each point you are allowed to move either in x minus 1, y or x, y minus 1 direction. Find the number of paths from point to origin. So let us try to understand the problem statement with the help of an example. So in this example, the value of x which is given to us is 3 and the value of y which is given to us is 0. So from 3, 0 we want to reach to 0, 0. So what we can do is we can consider this to be a matrix of dimension x plus 1 by y plus 1. And the reason why I'm adding 1 to x and y is because this is a zero-based indexing. So essentially, we can consider this to be a matrix of dimension 4 by 1. So what does it mean? Well, it simply means that there exist 4 rows and just 1 column. So let us make a matrix of 4 rows and 1 column. So this is row number 0, 1, 2, and 3, and this is column number 0. Initially, we are at this position. And from each position, there are two options which are available to us. Either we can move towards the left or we can move towards top. As we can see in this situation, the user has just one option, which is to move up. So this is just one path which exists over here to reach from 3, 0 to 1, because of which the answer to this problem will be 1 for this particular case, where we would like to move from 3, 0 to 0, 0. So that's about the problem statement, folks. Now let us discuss the optimal solution for this problem. So in the optimal solution, let us say x and y are the coordinates which are given to us. So as we have discussed in the problem statement, we can consider this to be a matrix of size x plus 1 by y plus 1. And let us assume the value of x over here is 3 and the value of y is 6. So what we can do is we can assume a matrix of dimension 4 by 7 over here. So let us create a matrix of dimension 4 by 7. So this is a matrix of dimension 4 by 7. And as of now, we are at this position and we would like to reach 0, 0, which is this position. So here is where we would like to reach. So rather than computing from x, y to 0, 0, what we can do is we can reverse the problem and we can rewrite this problem as we would like to compute how many ways there exist by which we can start from 0 to 0, 0 and reach to x, y. So what do I mean by this is, in question it is mentioned that we are at position x, y and we would like to move to 0, 0 and we would like to compute the total number of paths. What I have done is I have reversed this problem. What I am saying is that I would like to compute the total number of paths which start from 0 to 0, 0 and end at x, y. So these two problems are equivalent to each other, because of which if we solve this problem also we will get our solution. So let us try to solve this problem. So as you can see, when we were coming from x, y to 0, 0, the options which are available to us, so let us see, we are at this position. The options which were available to us is either we can move towards left or we can move towards top. When we were coming from 0, 0, the options which will be available to us is the opposite of this, which is we can either move towards right or we can move towards down. So what we are going to do is we are going to use this technique in order to compute the total number of paths from 0, 0 to x, y while moving towards either towards right or towards down. So let us compute it. So from here, as you can see, if we have to move to any of these positions, there is just one path, which is just to move to this position. So because of which I am calling that there exists just one path in all of these cases, because of which the total number of paths which exist for moving from 0, 0 to 0, 1 will be 1. Similarly, from 0, 0 to 0, 2 will be 1, and so on. So the first row will be 1, all ones. Similarly, when we are going towards down, there exists just one path, because of which all these values will be 1. Now, once we have populated all this data, the remainder of data is very easy to populate. What we can do is we can say that to reach this position, I can either come from this position to this position, or I can come from here to this position. So the total number of paths will be the sum of these two, which is equals to 1 plus 1, which is equals to 2. Similarly, the total number of paths will be over here will be 2 plus 1, which is equals to 3. Here it is 3 plus 1, 4, 4 plus 1, 5. Similarly, this is 6, 7, and 8. Now over here, the total number of paths, again following the same logic, will be 2 plus 1 equals to 3, 3 plus 3 equals to 6, 6 plus 4 equals to 10, 10 plus 5 is 15, and so on. So in this way, we will be able to populate this DP table, and the total number of path to reach x comma y will be how much? So x comma y we wanted to reach, the value of x is 3 and the value of y is 6. So the total number of path needed by 3 comma 6 is 84, and this is what we are going to return. So 84 is our answer. So that's the general idea, folks. Now what we are going to do is we are going to optimize this solution so that we could solve it in linear time. So in order to discuss the optimization of this problem, let us take this table and represent this table in Pascal format or in Pascal triangle format. So let us do that. So this is how we can represent this data in Pascal triangle format. So what I have done over here is to represent this data in Pascal triangle format. So let us assume this to be 1. 0, 0th element doesn't really matter. So let us start from 1 over here. So this 1 is over here. So this is 1, and then I have traversed this array in diagonal format. So this is another diagonal which I have traversed, and the 1 and 1 is over here. Then the third diagonal which I have traversed is this diagonal 1 to a 1, and the values are over here. Similarly, the rest of the diagonals I have traversed it, and I have kept the values over here. So one more thing, as you notice in this Pascal triangle, is there are certain numbers which I have represented in green colors. Well, those are the numbers which are missing from the DP table, but just for the sake of completeness, I have represented those numbers as well. All these numbers are missing. The one which are white are there in the DP table. Now, as we know that in Pascal triangle, if I have to represent a number, so let us say we are trying to represent this number. So 20, what we can do is 20 can be rewritten as in the format of NCR, and this over here, the value of n is basically the row number it is. So let us count the row numbers. So this is my row number 0, 1, 2, 3, 4, 5, and 6. So this is my sixth row. And which column? Well, the column number is 0, 1, 2, and 3. So, and if we solve this, 6 factorial divided by 3 factorial divided by 3 factorial, we will get 20. And that is how each elements of Pascal triangle can be computed using NCR. So this is the optimization I was talking about. So rather than constructing a DP table of dimension x by y, or rather than constructing a Pascal triangle, what we realize is in order to get to our answer, all we have to do is we have to compute this NCR. So far we have realized that in order to compute our answer, we need to compute NCR. So now the next question which we need to tackle is, what is the value of n and r? So now let us try to figure out what should be the value of n and r. So from our DP table, we know our answer is the last element of our matrix, right? So if the matrix dimension is x by y, then the last element, right? So the matrix last element of the matrix x comma y is our answer. So in order to find out the value of n and r, we need to find out what this value corresponds to in Pascal triangle, or we need to see where exactly in Pascal triangle this value lies, which is over here, and then from here we need to find out the value of n and r. So let us try to do that. So as we know, in Pascal triangle, each entry or each row of the Pascal triangle is coming from the diagonal of the DP table. So this is our diagonal number 0, this is our diagonal number 1, and this is our diagonal number 2, and so on. So in that way, if you want to find out the diagonal number of the last element, then that diagonal number can be given by x plus y, and that is the value of n. So the value of n is x plus y. So in this particular case, the dimension of the matrix is 4 by 7 in 1 based indexing. But since we have to deal with 0 based indexing, then the dimension of matrix will become 3 by 6. Now 3 by 6, then the last diagonal number will be 3 plus 6, will be given by 3 plus 6, which is equals to 9. And that the same thing is what we can get it from Pascal triangle, which is 0th row, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, and 9th row. So this is my row number 9. So the value of n is clear by now. Now what should be the value of r? Well, the value of r, which value are we trying to fetch? Well, the value which we are trying to fetch is the last value. So if x by y is the dimension, then the last value will be given by y. So the value of r is equals to y. So for instance, in this particular case, the value of x is 3, the value of y is equals to 6. So over here, the value of n will be equals to 3 plus 6, which is equals to 9. And the value of r will be equals to y, which is equals to 6. And in order to find the solution, all we have to do is compute NCR, which in our case will be 9C6, which is equals to 9 factorial divided by 6 factorial divided by 3 factorial. So let us solve this. So this becomes, and this if we solve, we will get 84, which is our answer. So I hope by now we are clear on two concepts. Number one, the first concept is, in order to get to our answer, we need to solve NCR. And the second concept is, what will be the value of n and what will be the value of r? Well, the value of n will be equals to x plus y, and the value of r will be equals to y. So in question it is mentioned that we need to return NCR modulo p, and the value of p is mentioned in the question, but the only thing to take from there is p is a prime number. So what we want to do is, we don't want to compute just NCR, we want to compute NCR modulo p. So let us see how we will be able to compute NCR modulo p optimally. So over here, in order to compute NCR, we are using Fermat's little theorem. As per Fermat's little theorem, if p is a prime number and a belongs to zp star, then a to the power p minus 1 is congruent to 1 modulo p. Please note the congruent sign over here. This is how we represent congruent sign. And also this concept is something which I have explained in a different video, where I have explained about RSA algorithm. So I will tag that video in the description. You can check it out and you will be able to understand what do I mean when I say A belongs to ZP star. It is not relevant for this video, but in case if you want to really understand what do we mean when we say A belongs to ZP star, that is something which I have explained in detail in that video. So let us proceed forward now. So from Fermat's little theorem, we know that a to the power p minus 1 is congruent to 1 modulo p. Please note, in order for this equation to hold, p has to be a prime number and a should belongs to zp star. Now what we can do is, we can multiply both the sides by a to the power minus 1. So let us do that. So let us multiply the LHS by a to the power minus 1, and this is congruent to a to the power minus 1 into 1 modulo p. Now if we rearrange this equation, this becomes equals to a to the power p minus 2 is congruent to a inverse modulo p. And rather than expressing it in congruent sign, if we represent this equation in equality terms, then this simply means is a to the power p minus 2 mod p is equals to a inverse mod p. So what does this mean? Well, it simply means is a to the power p minus 2, and if you divide it by p, the remainder you will obtain is equals to a to the power minus 1 modulo p. Okay, so let us rearrange this. So this simply means is a to the power minus 1 modulo p is equals to a to the power p minus 2 modulo p. And this conclusion is what we are going to use in order to solve NCR modulo p. So let us see how we are using this in order to compute NCR modulo p. So over here we want to compute NCR modulo p. Now NCR is essentially n factorial divided by n minus r factorial and r factorial, and then we want to compute modulo p. Now this is essentially equals to n factorial, and this becomes n minus r factorial and the inverse of this minus 1. Similarly, 1 by r factorial becomes r factorial and the inverse of that, which is minus 1, and then all these things modulo p. Now, as we have seen above, a inverse modulo p is equals to a to the power p minus 2 modulo p. So we are going to substitute this value in this equation, and then this equation becomes n factorial n minus r factorial to the power p minus 2 r factorial p minus 2, and then this entire thing modulo p. And this is what we need to solve in order to get to our answer, which is NCR modulo p. So that's about the explanation, folks. Now let us see how we have implemented this in Python. So the Python implementation is pretty much the same. So over here, as we have discussed, if n equals to 0 or m equals to 0, then the value will be 1, and that is what we are returning over here. So essentially 0th row or 0th column, then the value is 1, and that is what we are returning over here. Otherwise, this is the mod we want to take it with, and then the value of n is n plus m, and the value of r is m. So in order to compute NCR, we need to compute factorial. So this is what we have done. We have computed the factorial of n plus m and all the way till n plus m, and we have stored the value of factorial in fact array, and now we are using it. So essentially over here we are computing NCR modulo p, and as you can see, this is n factorial. Please recall from our discussion, we want to compute r factorial inverse of r factorial. So in order to compute the inverse of r factorial, all we have to do is r factorial, then to the power p minus 2, and then the mod operation. So this is what we are doing over here. And similarly, this is n minus r factorial and the inverse, and then all these things modulo mod operation. So that's the code, folks. Now let us go ahead and submit our solution. So our solution got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I'll try to address them. Thank you.